You know, this expectant hush kinds of tells me that you guys know it's 2 o'clock long before I did. It is 2 o'clock, so we might as well start the afternoon session. And as you see on the screen in front of you, our first speaker this afternoon is Matt Townsend, who is going to be talking about inter-operator transfer of signed TLDs. Thanks, Matt.
Thanks. I'm sorry, I'm not sending email during my own presentation here. I've just got a couple of presenter notes. For those of you who don't know me, I'm Matt Townsend. I'm a DNS operator at RightSide. For those of you who don't know who RightSide is, we're spun out of another company a couple of years ago, taking over Demand Media, taking over all of the domain and DNS related business that they had. So we are a few things that you might recognize: eNom, the registrar, name.com as well, some aftermarket sales, and a TLD registry. And it's some of the business of the TLD registry that I want to talk about today. In June of 2015, we transferred in what we think was the first DNSSEC signed TLD to move between DNS operators. And then a year later, we moved. So that was REISE, which for those of you who don't speak German, I don't either. It seems to be the word for travel. And then a year later, we moved JETZT, which translates to now. We were pretty sure that these were the first two to be transferred. I've been asking around for a little while, and somebody, I think it was Jim Reed, at the last IETF meeting, pointed me towards the Minds and Machines move to Nominet. I had a look at that, and it seems that all that was done there was actually a change of the glue records for the NSSET, and that they just forklift moved the entire infrastructure. So there wasn't really an operator transfer process followed. But of course, the way of things, I submitted these slides on Friday, and then about an hour and a half later, Carl Clements from Affilius told me that they have done a couple of transfers this year as well. So they did HIV in January of this year, and then a Japanese IDN sometime just after we did the JETZT move. So the two I'm talking about here are actually number 1 and number 3, as far as I'm aware now, unless anybody knows of any others. We'd really like to hear about it, because these are touchy, and knowing about other people's operations and experiences with this would be a huge help. So the sort of operational environment of TLDs is a little different from some other DNS operations, so I thought I'd just quickly run over sort of the parties that are involved in these things. So we have the registry operators. These are the organizations that actually hold the delegation direct from IANA. They're the organization that has the delegation. In a lot of cases, they will delegate the actual technical operation to a back-end registry operator. And then in some cases, the back-end registry operator might even redelegate some or all of the DNS operations to another party. So these are sort of the 3 levels of organization that tend to be involved in a move like this. In the case of a transfer, you've got gaining and losing operators in all 3 cases. So in the ones we've done, there have been a losing registry operator transferring their ownership of this TLD to a gaining registry operator. There's been the losing back-end registry operator transferring the registry operations to us, RightSide. So that's where we sit in this in these events. And then we also split off some of our DNS operations to ARI. So there's an actual fork in what the LBRO, the losing back-end registry operator, is doing, as they move some of their operations to us and some of the operations to ARI. And then, of course, there's IANA. So in the case of the transfers we've done, they've both actually been structured like this. Although there were different losing parties in both transfers, it's been the same 3 gaining parties. So we've had actually 6 organizations that we needed to coordinate for all of these transfers, which turns out to be complicated. So the ICANN policies for gTLDs, particularly the new gTLDs, specifically reference RFC 6781 for how to do a transfer from one operator to another. So these are the first 2 steps in section 4351 where the inter-operator transfer is described. So you have the initial state of the zone. So this is one operator, one parent, and what's actually being served in the DNS. The notation here is that anything with the _A or _B indicates the gaining or losing operator. So the _A is operator A, the losing operator, _B is the gaining operator. So records are appended with one or the other of those to indicate who generated that record. The RSIGs have the _Z or _K for the zone signing key and the key signing key. The RRSIGs indicate which key they came from, and then in brackets have which RR set that they're signing. So that's generally the notation here. In the case of the SOA records, there's an index number to indicate when the SOA changes. So you go from SOA _A0 to SOA _A1. So the first step here is going from the initial state to the pre-publishing state, where nothing really changes at the parent, but both of the child zones, both the child operators publish each other's DNS key set and then sign the joint DNS key set, and then share their DNS key covering RRSIGs with each other and pre-publish those. So there are actually 2 steps of sharing data that have to occur here in order for this to work. They first have to share the DNS keys, then generate RSIGs, then reshare those, and then they can pre-publish each other's data. At the same time, child A will add operator B's NS set to the zone, so that will start moving some traffic towards the gaining operator. After waiting for the appropriate TTLs for all this stuff to wind up being fed into everybody's caches, go on to the actual redelegation. At this point, nothing changes at the children, but you ask the parent to change the NS set and the DS records in the parent zone. Again, after waiting an appropriate period for all the right TTLs to expire, then effectively at that point, all the traffic will be moved over to the gaining operator, and you're done. They can then stop publishing the other operator's keys, and you're into a new steady state. So it's fairly straightforward. The difficulty is if you are a TLD operator, or really anyone publishing your zone from a database or any other automated system, this doesn't really work very well. There is no easy way in the way you would generally transfer a system like that to actually share data back and forth bidirectionally, or to have the different operators publishing different versions of the zone at the same time. So for example, if you're trying to take a database and generate that into a zone, you basically have to modify your zone generation software in order to easily reinsert RRSIGs from another operator, particularly since a lot of signing software will strip RRSIGs that already exist in the zone as it goes through to do signing. And you can't just do something like replicate the database between operators. In the case of TLDs anyway, that's moving that database from one operator to another is very complicated. Usually takes a couple of hours each time you do it. So, in order for us to do these transfers, we had to come up with something new. So for the REISE transfer, we came up with a procedure that we thought was going to work. This is essentially what we did. In the very first so the operational setup here is that we started at the initial state by doing by setting up zone transfers between the losing operator and the gaining operator. so that we could get onto our DNS infrastructure exactly what was being published by the losing operator. And that's sort of the assumption through the entire thing here, is that zone transfer is what is getting the data onto both sets of name servers. And so what we did is we generated keys that we would be using in the future and passed that DNS key set back to the losing operator for them to pre-publish in their zone. They sign that, and we wait for TTLs. And then we went to IANA and asked them to insert the new DS records into the zone, into the parent zone, into the root. So this would allow people to start caching that. Once that was out there, just for notation here, to make these easier to follow, I've moved the last step from the previous slide to the first step in this slide, so you can easily see the difference between them. So going from the first DS change, we start moving traffic. So we update the NS set in the child zone. Once we update the NS set in the child zone, and I have a notation error in here I've just discovered. We should still be pre-publishing DNS keys at this point. Those did not actually disappear. So we start moving traffic from operator A to operator B. Once we see that traffic has appeared, we go to IANA and ask them to please change the NS set at the parent. So sort of at the end, once waiting for TTLs at the end of this redelegation step, we have the losing operator still generating the zone and still signing the zone, but all of the traffic, all of the queries are actually coming to the gaining operator to be answered. So after the redelegation was done, we moved signing. So basically what we did was turn on signing at our end, which strips all of the DNSSEC material from the zone that's being generated by the losing operator and replaces it with ours. And then once that is done, once again the appropriate TTLs expire, we go back to IANA, ask them to change the DS record or pull the old DS record. And at the end of that, we're basically done. At this point, all we're doing is at the end of DS change 2, we've got old DS keys hanging around from the previous operator, but that's really it. You can pull those, once the right TTLs have expired, you can pull those at your convenience, which we did and wind up at post-migration. So this ended up being a really, really long process, particularly since there were 2 interactions with IANA during this. So IANA works quite well, but they do have a varying workload. And so a request to change DS records or a request to change NS records at IANA, I've had them take a full business week, and I've also had them come back in less than 48 hours with a modified root zone. And it's hard to tell in advance which you're going to get. So when you're doing planning for an operation like this, you sort of have to assume that it's going to take a week and deal with that appropriately in your timelines. That uncertainty is kind of difficult for some business people, but it's something we have to deal with. But at the end of this, we sort of concluded that we were being overly cautious in this process, and that we could have done it a lot quicker and with a lot fewer steps dealing with IANA. So a year later, when it came time to do the transfer for JETZT, I sat down and worked out a different process. So this one is actually a little bit closer to 6781 in terms of the order that things happen in. So we went from the initial step to pre-publishing DNS keys on the losing operator's name servers, and immediately changed the NS set. So because we have the zone transfer going through, all this data shows up on the gaining operator's name servers at the same time. And that works out fine. Once we've got data actually showing up and we were comfortable that was all working, then we go to IANA and ask them to please change the NS set for the zone, and add the new DS records. So this completes moving traffic from operator to operator once those TTLs expire. After this, no new traffic should show up on the losing operator's name servers, and gets the pre-publish of the DS records going. So moving from the redelegation to the signing transfer, at that point, once TTLs have expired after redelegation 1, we could move signing. So the losing operator essentially stops signing, the gaining operator starts signing, and we switch which DNS keys we're using to generate RSIGs. Again, waiting for the RSIGs from losing operator to expire, we can then go back to IANA and ask them to remove the old DS set. And at that point, we're done. This was a lot quicker. Only 5 steps instead of 8, and only 1 interaction with IANA. However, we had some more operational problems with this one. So the process itself worked quite well. But we had an operational issue at the losing backend registry operator where they had deliberately modified their name server to exit if it encountered a DNS key for which it had no private half. This was in response to an error they'd had at some point in the past where an HSM died and their name server went on happily failing to sign things without them noticing a problem until it was too late. So they had made this modification, but which had the undesirable side effect that it was impossible for them to pre-publish another operator's DNS key. So as soon as they insert that public key into the zone, their name server software would fail to load the private half from their HSM and exit. It's also had the undesirable side effect that it seems like adding their name server actually managed to do a zone transfer out before exiting. And they wound up with a situation where they had pre-published DNS keys but an old RRSIG over the DNS key set in the public name servers. And this caused validation failures for a couple of hours until they were able to fix it. But overall, this worked out a lot better than our previous attempts. So the things we picked up from this, number 1, planning in detail. This is fairly obvious, I think, but we ran into stuff that we wouldn't have thought about in advance. So for example, the fact that we had 6 different organizations that we were trying to coordinate for several of the steps that we had to do. And that was 6 different organizations in 5 different time zones. It meant that sometimes simple things like, Party A makes a change, Party B has to check to make sure it was made correctly before okaying the next step. If that change happens after business hours for Party B, especially on a Friday, then you might be waiting a long time for the next step to occur. And we ended up having to factor this into our planning quite a bit. Ultimately, that alone added about a week to this whole thing. Obviously, operators really need to test procedures, but the real takeaway here is testing procedures that you don't even think you're going to need to do eventually. Our biggest hiccup here was caused because the losing operator had never really planned on losing a zone, and had never looked into what they were going to have to do in order to get through that cleanly. So they didn't know. They didn't actually know where the sharp edges were in their software because they had never tested this. We actually ended up in doing this sort of testing for a new infrastructure that we're building. We found a similar problem in a different implementation where it's perfectly capable of pre-publishing, but only if you modify the key store by hand. The tools for adding a public key or the tools for adding a key to the system won't allow you to just add a public key. You have to go around it. It's an easy workaround, but if you don't test in advance, you don't find out that it's going to happen. So given what we've had to deal with here, and given that the gTLD namespace is continuing to expand, there are tons of new operators, many of them without real experience in this area. And a lot of people who have lots of DNS experience, but maybe not experience at operating TLDs, who are now operating TLDs. We sort of felt that it was a really good idea to have some really clear advice out there that people could actually follow. Right now, ICANN's advice that you follow RFC 6781 doesn't work, and we need something else. So we've actually started working on a new internet draft to describe the second procedure that we followed, which we think is sort of the best case at the moment, when we're hoping people will contribute to that, comment on that. So there are a couple of links here to where that's being tracked and edited. So, yeah, does anyone have any questions or comments?
Lots, apparently. So you made a comment a dozen slides or so ago, I fell asleep, where you said that we moved this and there shouldn't have been any traffic anymore. Did anybody measure that?
Yes.
So there wasn't any traffic anymore?
According to the losing operator, because I don't have direct access to their systems, their query rate had dropped down to tens of queries per minute.
So there was traffic.
So there still was traffic. There shouldn't have been traffic. It was traffic that I think we waited way longer than the TTLs said that we should wait for this. I think it was about 48 hours.
Okay.
And at that point, we figured the only people sending queries to those name servers were pathologically broken.
So I asked that question for two reasons. One, I was involved in a move several years ago, and decade and a half later, there was still traffic to the old address. And somebody else moved about 10 years after, or actually about 5.5 years after we did, and they're still getting traffic at the old address.
Those are both root moves?
Yes.
Yeah.
And, but if, in this instance, you're saying that there was still tens of queries per second, per minute. I think that Jeff, in his spare time, might want to investigate, because there seems to be this sort of residual, sort of reflective background traffic to phantom things that don't exist anymore or shouldn't exist. And I've never got a satisfactory answer as to why that happens. And I'm kind of surprised it still does. The second question is...
Can I respond to that before you move on?
No.
Okay.
Oh, sure, you can go ahead. Go ahead.
So I have renumbered a couple of TLD servers in the past and encountered the same thing. I sort of understand some of the traffic that continues to show up at root servers because people have old hints files and things like that. That probably doesn't account for the level of traffic that continues to arrive at those servers, but would account for some of it. The thing that I've always been confused about is at the TLD and further down the tree, where people are getting the addresses from that they're actually sending these queries. And it's a little bit unrelated to this, but another thing that I noticed at a previous TLD that I was operating, we received a tiny but measurable, but consistent and measurable number of queries for TLDs for which we were not authoritative.
Yeah.
Yeah.
It's like...
and I think it's all related, but I don't know what the mechanism is.
They're all like the weird aunts and uncles that you keep in the closet. So the second question, there is, Dan Massey doesn't come to these things anymore, but he in early DNS sec days, there was this construct called Islands of Trust, where you could, in fact, take trust anchors at various points in the hierarchy and install them locally. When you do these kinds of transfers, how do you deal with people who have taken the old keys and put them in their local TA cache?
We didn't.
How do you deal with that?
I don't know. In this particular case, I guess it wasn't a conscious decision, but I guess we decided to just not deal with it. And I think the reason for that is that these are all TLDs whose existence postdates assigned root. And it seems to me that there's a really low likelihood that anyone has bothered with islands of trust for these. If they have, I can't think of a good operational reason for them to have done that. So for these, I don't think it's a problem. I think that's definitely a problem if we were to move, .org or anything else that was signed prior to the root being signed. I think it's less of a problem for these.
Paul Hoffman, on your previous slide, the last bullet on slide 13, the last bullet you didn't mention. Can you say a little bit about how that happened?
Yeah, I'm sorry.
No, I'm just really interested from the ICANN standpoint of how PDT can get in the way of things.
Yeah, sorry. That was I did intend to skip over that. I think this was a side effect of the fact that REISE was we still think the first signed TLD to be moved. It's certainly the first new gTLD to be moved. It seemed like both us and ICANN weren't entirely sure how to proceed on a couple of occasions during the planning stages. So we had submitted, there's a requirement to submit a transition plan and have that approved. We had done that. Our transition plan included dates for when the move would begin. And we had gotten to the point of, let's see, we had submitted the DS change, I believe. Oh yeah, and in this first stage, we actually did things in a slightly different order. We had changed the NS set already in the parent zone, and ICANN came back and asked us to please do PDT. So we had to back out. So the DS change request was canceled, and we reverted the NS set at the apex of the zone, and then had to sort of unconfigure everything in order to switch over to generating a PDT zone from our registry rather than zone transferring from the other registry.
And that didn't happen a year later when you did
Right.
JETZT.
Yeah. When we came back to do JETZT, the process had all been smoothed out, and and we knew in advance this time that we were going to have to do PDT, so we factored that into the plan and made sure we knew when ICANN wanted us to do it. And
Okay, great. Thanks.
Amanda Swain from Sarah. So we've also been undergoing some of the same transitions, and one of the things that we're finding is that as we're doing more of these kind of operator transfers, that the complications involved. So one of our back-end one of the DNS operators, for example, have offline KSKs, and so when you have multiple transfers happening, for example, that really delayed what we were trying to do, and that they couldn't sign that DNS key set because that only happens once every 3 months. So thinking about that as that happens more and more for other people and looking at DNS operators, that's something to take into consideration, both for your own infrastructure and when you're working with someone else.
Ray Bellis here, actually channeling Brett Carr from Nominet. Said they'd be very happy to discuss with you the sort of transitions they're doing on the minus machine stuff at the moment. I believe they've got sort of 26 of those in progress due to finish in December, and also happy to review your draft and cooperate wherever they can on that.
Thank you very much.
Dwayne Wessels from VeriSign. So since you asked at the start, Matt, I wanted to mention that .gov was transferred in January 2011 as a signed zone.
All right.
Yeah.
No other questions? I'd like to thank Matt.
All right. Thanks very much.
I'm looking for Chris. He's leaping to his feet. So next is Chris Baker to talk about DNS performance metrics.
Good afternoon, everybody. I'm Chris Baker from Dyn, and today we're going to be talking about DNS performance metrics in a little bit of a different way than probably previously so far in this conference. Because so far, it's been about us measuring ourselves, and this is about this group of others measuring the DNS. Now, the word others is chosen here because realistically, I think the variables being considered by other people measuring measuring the infrastructure that we operate are different than the things that we consider. So, everyone here is here because they love the DNS. It's Sunday, you could be relaxing at home, but you're here with us, and it's a great time. So you're kind of used to these ideas of when you're operating the DNS, there's a number of factors that influence its performance. There's provider issues, there's packet loss, there's stress on machines. But let's ignore that we know any of those things, and let's think about how right now, if we were to try to make a DNS decision, we'd get information. So I myself, not being very creative, the first thing I'm going to do is I'm going to go to all the different search engines. So to be equal in this case, we have Bing as well as we have Google, and we ask them a question, and they both give us a very similar result. If I want to know about DNS performance, I go to this website. Okay, well, maybe if I'm a little bit more advanced and I have some more roots into the community, I'll check some mailing list threads to figure out what are people on mailing lists recommending. Well, here's another website. Okay. Now, we usually go to tools like DNSMon and Write Atlas, or if you're lucky, the Analog Ring, because these are operator-run systems that allow diverse collection of types of metrics, as well as different types of interactions with systems, because we have a multidimensional understanding of the systems. However, there's also a whole suite of other things measuring the DNS that might not be in our purview that we might want to consider when we're thinking about how other people are understanding these systems. So today we're going to go through how a bunch of these different systems work, and then how that kind of contrasts with our mental models of the DNS. Assuming that I know all of your mental models, of course. Now you might be asking, why does this matter? So for the other providers in the room who do authoritative DNS services, people might come up to you and say, why aren't you #1 on random website X? Now for other people, that's not of concern. So there's the contrast of, well, if other people are measuring the DNS, maybe they have some insights into things that we haven't thought of. Maybe they have some methodologies we could learn from, or maybe some pitfalls we could check and make sure aren't manifested into our systems. So that's kind of high level of what we're going to go through right now. So, being a pedantic data nerd, the first thing you do is you go out and you write a little headless browser thing to go collect data from these websites on the rankings. Now we've left names out because the goal isn't here to look at names, it's to look at data and how these systems are being quantified. So the two free providers on the internet, we go and we crawl their websites and we take their rankings and we smash them together. Now the first thing you notice is, hey, wait a minute, all those numbers don't match up. For ranking #2, there's no #1. So it turns out the consideration set of providers between these tools isn't the same. Well, even within that is kind of interesting because we're not looking at the same base populations. So the people running these tools are thinking about things slightly differently. The other thing that stands out is these rankings are just completely different. There's very little alignment between them, and that kind of causes confusion, because if I'm trying to make a data-driven decision, one would hope you could go to these things, compare the indexes, and then from there have some rough understanding of what is good and what is bad. So we'll go away from just looking at number rankings, and we'll look at quantification of service numbers. So in this case, we left the names on because things just look crazy all over the place. You have one set of measures of what is called a query time compared to another query time. And when you look at the difference, sometimes it's multiples of one of the observed values. So no matter what provider you are on here, you can look at these numbers and you can say, something confusing is going on there. And the way these measurements are being collected must be interesting and nuanced, because it's not something you'd expect to see such wild deviations. So let's consider the platforms and what you're considering when you're actually going out and getting this data. A lot of the times we take these geomaps because we want to show people the diversity of the places from which we're taking samples. This is a good thing because it turns out speed of light is a factor. However, if we're just thinking about spots on a map, we're kind of losing some nuance of network performance, as people talked about earlier in the Anycast presentations. So if we think about it, one of these services is using 25 measurement collection points. Now contrasted to Write Atlas, that's not that great, but this is also somebody who's taking their time to operate infrastructure to measure the DNS for everybody for free. So we don't want to criticize them too harshly. Then after talking through them and going through their pages, we look at their methodology. So in this case, they're using dig. They're digging for each of the name server records presented from each provider, from each location, and they've made some modifications or specialized flags into the dig command. So they've thought about this, right? Like that's a signal. The fact that they've changed the defaults means there's kind of some reasoning behind tweaking them. And from that, we can kind of extrapolate some small things about what they're trying to isolate in the collection of these samples. Their testing duration is once every 15 minutes. And this is a theme that'll come up again and again on how frequently we think we all need to take measurements of the DNS to have good conclusions about its performance. And the other wildly divergent notion is what we should use for timeouts. Now, in an ideal world, we wouldn't have to think about timeout duration because it should never happen. But it turns out from all these different timeout durations, it's kind of interesting. So provider 1 in this case has set their timeout to be 2 seconds. Now, in most of these measurements, what they're doing is they're taking a measurement from an infrastructure provider against the authoritative name server. Now, to everybody in this room, that may or may not make sense depending on how you're thinking about caching semantics. But if you think about it from somebody who's completely outside of our universe, is this something that needs to be explained to the consumer of those original data sets? And are they going to be able to contextualize that within this data to make a more informed decision? So to anchor it in reality, we see CDNs take these type of measurements against our authoritative network regularly. So you could contrast that data set and say, okay, this makes sense because their infrastructure is talking to our infrastructure regularly. Okay. But again, it's going to come down to the case-by-case scenario of the end user of the services. So if we think back to that diverse map that we saw originally of places in the world, and we contrast that to the types of maps that the internet manifests itself, of how these places are actually connected to the internet, things get a little bit more interesting. So instead of looking at countries, we look at the connectivity of these different providers. And later on, we're going to see an example of why this connectivity element matters and how the notion of how we should think about the way this is exposed to the consumer of these metrics. Because these are really important things that all get rolled up into a single summation of server performance that is kind of garbling up some important bits. So we look at another a free service provider from column 2, and they state their measurement locations but don't provide a count or a map, which isn't a bad thing. And instead of using dig, they're using a PHP library. Now, I wasn't sure how important this was to other people, so I figured I'd include it because it's a great way to get some feedback on if people know about issues with this. Because dig being well accepted and regularly used is good. I've personally never used this PHP library. Maybe one of you know about a nuance with it, which is not the best. The thing that's interesting about this tool is their sampling duration. So in this case, you go to the tool's website, you enter a domain, and it collects DNS timing information. Now, the sample range is over a month, and then from that month, they then create summary statistics. So there's no guaranteed frequency, and there's no guaranteed number of tests that are run. Yet at the same time, we're posting a number that's contrasting to something which is measuring on a regular interval. So statistically, very different ways to look at the same thing, which most likely are going to produce slightly different results. The initial case that came here is the first thing you do when something is broken is you go to isitdownornot.com, or you run to the site and enter it in. So you could be having a sampling bias of things being worse or better depending on your end users. So then we enter into the maps with many more dots. And these are the enterprise class measurement systems. So these ones boast numbers like 500 plus nodes on backbone, mobile, wireless. They have flags for IPv6. And this is where we start to get into a place where there's a very rich set of measurements. However, it's taken with proprietary tooling. So understanding some of the semantics of how the queries are issued and received is a little bit nuanced and hidden. In the case of this service, they kind of have an interesting thing where when they're taking the measurements, they take 3 measurements every 1,500 microseconds. And if nothing is returned after the 3rd attempt, they'll mark it as a failure. However, on the event that there isn't a response, the response equates to a 1,500 millisecond response time. So sometimes when you're looking at this data and you see this anomalous trend that's manifested, it's not actually part of your performance. It's just the way they're handling error conditions. And this is really fun to figure out when you don't have that piece of background information. And yet another platform. So in this case, they've glued together some very interesting notions. They have a third-party platform that they're using to run the measurements from, using DNS Python. They have 250 of their own independent test servers, and they're using RIPE Atlas measurements. So in this case, we're measuring from all these different systems and gluing them together to make conclusions. Okay, so we've talked about all these things. Why does this matter? Well, the first thing I wanted to do is go out and use RIPE Atlas to collect some data sets which would make cool anomalous patterns. Because if I'm in the business of making metrics, the best thing I can do for my end customer is show them how I found something wonderful that is going to completely explain to them the value of my service. So in this case, I commissioned a bunch of RIPE anchors to measure against our name servers, and this is what we get. What is going on there? All of a sudden, during one part of the day, there's these anomalous spikes in round trip time. Must be an issue. So if I were to take this blind and not research it and average it in, I'm going to be hurting the perceived performance of our platform. But as operators, that's never what you do because you didn't do anything wrong, and the internet itself must be wrong. So, because we're proper scientists, we're running multiple collections at the same time. And we can see that of them, only one is seeing this anomalous round trip time pattern. Okay. Now, before the corrections come in, we were also using hostname.bind to track the endpoint, not NSID. I apologize. I'll look into fixing that in the future. I'm sorry, Dave, we could have done it the right way, but we didn't. So right now, we have these contrasting measures, and we can see that something is wrong. Now, this is where the line is drawn for a lot of these measurement platforms because they're just designed to produce rankings and numbers, not actually solve problems like the tool sets of operators. And that's not a bad thing because it turns out for a lot of people going this deep down the rabbit hole might not be productive or even worth their time. But of course, as network operators, you need to know what is happening there. So in this case, it turns out during daytime hours, there's a hop between Sparkle and Tata that there's either a saturated link where all of a sudden you go up by 100 milliseconds of latency every day on a fixed cadence. And it's still occurring today, so if anybody knows anybody there that would like to talk to them, I have plenty of details, or they can measure it themselves. The important point being here, getting down to this level of root cause of why that metric, that round trip time metric was being elevated so high, is something that an operator needs to do. And if the person taking the measurements isn't considering all these different hops between providers, it makes a strange case for what we're measuring. Now, we all know the most important thing to consider is what is the thing doing the querying, so how long is it going to take eyeball users or other machines to find DNS records. But in the case of somebody producing summary statistics and publishing them en masse, it's not as heavily considered. So, now we're going to go over some observed issues and hopefully collect some wonderful feedback from people in the audience on all the things that I've missed. But this measurement granularity. So we saw 5 minutes, we saw 15 minutes, and then we saw monthly aggregates. How often do we need to be measuring these things to get the types of results to make authoritative statements about rankings and performance of things on the worldwide internet? Then there's the notion of averaging. Do people find averaging performance across all 4 name server pools to be an appropriate thing to do, or should these be individually manifested and tracked? Again, a notion of nuance and a notion of expense when you're thinking about storing the data for producing these metrics. The network awareness and packet loss issue, a lot of that I think comes down to the complexity of the platform. So if we're just running dig commands from different cloud providers and collecting numbers, that is one way to do it. However, then in some cases we're going to be attributing network performance issues to the provider, which might be okay, because then it might be a selection issue of, well, maybe you should have chosen better providers. Now, in other cases, you'll see from the collection point continually growing numbers for all providers, in which case it suggests that maybe it's the egress of the measurement point that is having issues. But again, these are all things that are nuanced to operators and might not be popping up for all the people who are in the end going to be consuming these data sets. Proximity controls is a fun one, because of course when somebody else's service is beating your service in a specific locality, the first thing you have to do is figure out why. And when you can quickly fingerprint that to them being closer, well, throw your hands up because the game's rigged. The assumption about timeouts, I would love to hear people who've studied this in depth. I'm sure people have their opinions on the ranges chosen. So guidance, this is where we get a massive line of people telling us how we should be doing these things, because isn't that why we're all here? To provide feedback to other operators about the way things should be done in networks, so we can all stand on the shoulders of giants. So, One of the people who suggested that you should always be taking the ping measurements alongside your dig measurements or your DNS Python measurements, that was a really great suggestion by one of the enterprise providers. The problem with replicating some of this regularly using Write Atlas is just the cost of credits. I think I blew through 7 or 8 months worth of aggregated probe credits in about half a week. Credit issues. And then, how important is this notion of making measurements through authoritatives versus recursives? And this is a question I think that is going to be really interesting to a number of providers, because as you start to test it more, it really becomes so nuanced to the consumer of the data that doing it generically just seems wrong. And I would love to hear other people's contrasting opinions to that, because the smoothing effects that we saw when we took that same set of really rocky measurements and we ran it through the recursive was this nice smoothing behavior because of the caching semantics of the records, which might have been the end user's observed performance versus our synthetic performance. And then, last but not least, how do operators want to define this notion of availability? So some of these metrics providers also post this thing called availability. And if they query a name server, and that name server doesn't, an individual name server record, and they don't get back a response or it's lost, it impacts a availability metric. Now, if any of the name servers were to respond, is that how people think that should be measured? I think it'd be a really great thing if we could come together and kind of put together a manifesto of how operators think these things should be measured with our great nuanced and in-depth views, so we can hand these things back to people taking these measurements to make things better for everyone. So, if anybody has any questions, comments, concerns, or corrections, I would love to hear them.
Bill Manning again, and I sat close to the mic so I could do this all afternoon. So the question of timeouts is interesting because I equate that to things like TTLs. What is the standard TTL across the worldwide internet? Because your selection of timeouts really ties to what the TTL is. And I've seen TTLs as short as a second, and I've seen TTLs that effectively are permanent. So your selection of timeouts, I think, really needs to know a little bit more about what the TTLs are.
That makes sense. I'm not emailing either. I'm just taking notes on what you're saying.
Oh, I just figured you were playing Candy Crush.
I'm more of a farm guy.
TMI.
I'm getting kickbacks from the live stream.
Somebody's getting kickbacks, it's not me. So the second thing that I had sort of a thought about was that you were asking a question about authoritative, measuring the authoritative versus through the recursives. And I grew up with the idea that we will answer any query we receive, right? So that's from an authoritative standpoint, that's really kind of like, I don't really care about the intervening infrastructure. I don't care about the, how badly configured the caches or the recursive resolvers that I have to step through to get to the client. And so if the authoritative server will answer every query it gets, the question then becomes, for me, how do you instrument the far end of that? Not the recursive, but the end node that's actually initiating the query in the first place. I don't know how well we do that, or if anybody has a good idea about how to do that. But from a measurement perspective, I think we need that data.
So aside from the work that the APNIC folks do, there's actually another interesting free platform, TurboBytes Pulse, that I think I've seen Jared mention on a few mailing lists, that does some DNS rum beacon timings. So if you're interested in taking a look at that, they've orchestrated a system. And at Dyn we also do some rum beacon timings. So people are doing it. I don't know how accessible all the data is right now, but if you'd like to follow up, I'm happy to.
Thanks for doing this. This is interesting. I guess the comment I had is that usually when I get forwarded, one of these customer inquiries from support or wherever it goes about, you know, I saw your rankings on such and such a site and it looks really bad. Why is that? Frequently when I go to investigate, I discover that they're doing something really simplistic in order to produce their number. And the biggest complaint or the most frequent complaint I have about them, I guess, is that they're not really taking resolver behavior into account and doing something like checking, you know, querying the entire NS set and then averaging that into a single, you know, average RTT for that test and then moving on, you know, to the next test. You know, which obviously doesn't, that's not how the DNS actually behaves. And yeah, the thing I'm always end up having to say is, well, yes, that number looks bad, but it's because they're doing this and it's not, you know, it's not what you would actually see from where you are, kind of this sort of thing. And I don't know how to feed that sort of information back to the people who are writing these tests. There just seems to be a lack of nuance, I guess, that they need to find out about somehow.
So I guess, as another operator, do you have concern about the existence of these things? And do you think it's something that, you know, we all as, you know, as OARC members, as internet operators, should try to standardize and communicate? Or is it more an educated consumer will do the work to find?
Yeah, that's hard. Yeah, having somebody like OARC doing it is tricky because there's, you know, issues with members and all that kind of stuff. I think maybe what I'd like to see is somebody who is knowledgeable enough about the DNS, who is, but who has less of a less of something commercial to gain from the numbers themselves, producing a service like this. And I don't know who that would be, right? Like most of the people I know who I think would give this would generate a service like this in an actually fair way would appear to be biased. And so yeah, so I don't know who it is that would do that.
Oh, thank you very much.
Gustavo Arzola. I've been on the consumer side of this, and oftentimes people want these measurements because they're trying to solve a problem. And they use these measurements because they have no other way of understanding what the problem is. And from my perspective, what people really want is, if you're seeing this, do this. If you're seeing this, do this. And these measurements are a substitute for, I can spend some money to fix a problem because I don't know how to fix it, I don't know what it is, and that's all I can do.
That's great feedback. And so, as somebody who's used these services, do you kind of like dig around and look for tools to do more advanced diagnostics, or is it more that the problem is fleeting enough and not worth the time to you know, to dig down to that hard root cause analysis?
In my case, I did a lot of research, but it was very frustrating because I only cared about two things. I wanted to know how my customers were able to get my site, and I wanted to know how my people at my own office were able to access the internet. And it all begins with, can you resolve a name? And the delays are usually, from people's perspective, is the page isn't showing up, and when you do the measurements, the name's not resolving. And I don't have any control of that. And so these measurements are sort of a quality gauge, because I have nothing else to understand what's wrong unless I do this deep dive and start getting into things.
Oh, great. That's great feedback. Thank you.
Hey, Varric from Cloudflare. This is not really a question, but maybe a follow-up on the previous comment. From what I get most of the times, it's not really a DNS problem, it's more like a networking problem. So maybe the part of the blame for unfairness is not on the providers of such services, but maybe it should be the consumers who should be more educated to at least say, show me the performance in these big eyeball networks I care about, and we'll just then different numbers.
And I think you're spot on when it comes to network performance, but I think from the consumer's perspective, they're oddly collapsed down, and it's almost an expectation on the service provider to have understood the networks that they're on and how anything might get to them, which of course is a pseudo-impossible task. But yeah, it's, I'm nervous about the educating the consumer side because we don't seem to have done very well with the Internet of Things problem, and that one's in a sense like much more scary. It's kind of like the tragedy that comes with pollution. Like we can't get people to recycle, so how are we going to get them to care about network performance? That's
That's a fair answer, but at the same time,
no.
if you compare how the service number 1 looks and how the service number 3, which we both know who it is, works, then it's the usability of both services is kind of different, and the third one at least allows you to pick a vantage points or eyeballs where you care about.
Yeah, if you want to trade cards after and look into this with me, I would love to work with some other people to get some feedback on how we could at least try to help.
Yeah, sure.
Great, thank you.
Thank you.
Hi, I am Ciprian Cosma from Amazon. I think the problem is people try to measure two things, one on top of the other, just like you said. One is the customer experience, and one is the operator health and performance. So an interesting experiment would be to measure from these probes both the time that it takes from the local recursive resolver and the time that it takes to manually go out and get the result, to see if your ISP is slow or the actual DNS provider is slow. I wonder if DIN does something like that or not.
So as a side project for kind of qualifying some of the population of Atlas probes, one of the things I was doing is seeing how many of them are using the on-ISP resolver versus going out to Google and other places, because it turns out those networking issues introduce a whole other very interesting area of not randomness, but just a big source of error. And very similar with cloud providers. Like there's some cloud providers that are using, Google public DNS. So then all of a sudden you have another interesting path of, where is this query really going? And then back to the education issue, if you think about all the different hosting companies and where all the different resolver sets that they're using, I think you're right. It's definitely two specific measurements, and then within those,
or maybe three, as you said, one to your default, one to Google, one to the actual, to see what's going on.
So if we get a gradient of the most frequently used resolvers.
Chris, that was actually a question I was going to ask you as well. That, if this is a consumer issue, why are these folk asking the authoritatives? And the follow-up was, if you redid their tests asking the local recursives, would you find almost a complete differing of priority, that the ones that are ranked worst by asking the authoritatives come out just fine when you ask a local recursive provider?
Yes.
The customer experience differs by how much?
Well, yeah, totally. But I mean, Dean wants to know what they have to do to improve the customer experience by improving their own infrastructure. So if you measure them together, but if you measure them separately, you can do diffs between these measurements and maybe learn something new.
Well, and I think the point that Jeff's kind of leading us to is, if you start to then tune your performance to win these tests, you end up degrading net performance. So it's like, to win the athletic competition in the Olympics, I'm going to just start eating at McDonald's every day and drinking Coca-Cola, because that's what's going to make me win.
Well, there is no proof. There is no proof that they go in separate directions. Maybe by winning this competition, you would improve the customer experience. I mean, how can you tell that you would degrade? Yeah, never mind.
We'll trade some cards and check it out. Thank you all for your time.
Thanks, Chris. Now, I'm not sure who's giving this next presentation. Someone from Cloud. It's Marek, is it? Oh, okay, and Jaime, was it? I'm not quite sure. Thank you. This is on a skeleton key in the DNS, exploring something. CVE 2005-7547. I have no clue, but I'm interested to find out. Thanks.
All right, hi, my name is Marek. I'm one of the two names on these slides. This is my colleague Jamie Cochran, and we both work for a security company called Cloudflare. This is a little bit different from what we do every day, so I thought it might be kind of fun to share it. If you remember last year, there was this fun, peculiar bug in the gRPC stub resolver that could potentially be used to do remote code execution in DNS clients like browsers, SSH, and pretty much everything that runs on your personal computer. So here we go. In the first part, I'm just going to walk you through the basics, like what the CVE blah, 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 blah is, how to carry out the attack. And in the last part, I'm going to pass it to Jamie, who's going to say a little bit about mitigations and the security aspects of the thing, since that's not my area of expertise. So, as I said, it was a vulnerability in the gTLD DNS client. That's the stuff that's deeply embedded in like every application there is, except maybe the Golang ones that have a Go implemented bindings. It was kind of similar to the previous vulnerability that happened in the past year. It was called Ghost because it existed in the guest host by name that's supposed to be misused or discontinued. What's kind of interesting about this timeline is that it was reported way back into 2015, and the disclosure and the actual fix happened like 7 or 6 months later, which is a pretty long time in software world, and it gives you the idea how much attention does this stuff get. Another interesting thing that happened is that there was a POC on the same day, so that kind of lowered the barrier of entry for lower level attackers. Everybody could exploit their thing without writing a line of code. So naturally, it gathered some interest and spawned a bunch of blog posts and articles. One of them was interesting from Dan Kaminsky, who called it the skeleton key of unknown strength, which is kind of fitting to this particular vulnerability. I'm going to explain why, but first, let's have a look at what most of the attackers do. So in the bulk of the attacks we see, they usually target servers. This, if you pardon my art skills, this guy on the left is the attacker, and this cloud on the right is the bunch of servers. So what do the attackers do? They find out about the latest remote crasher or RC or any sort of bug and exploit it with the specially crafted malicious query. So what goes on? The server goes boom, and nobody's happy, but the customers are, or the DNS clients are not really affected, except that they might not get serviced. What happens sometimes, and especially before the Kaminsky bug, is that the attackers could just flood resolvers with spoofed answers, and which would be passed on to the clients and redirect them to a spoofed site. Like this bank is not my bank, but it's an attacker trying to steal your secrets. Sometimes they're smart and they combine these two attacks. So first they attack the authoritative, so they make it unavailable to the recursive, and then they have plenty of time to send their spoof traffic, which could get back to the clients. But in all these cases, what do they have in common is that they don't really speak with the clients directly, unless they're doing man in the middle or something. But in this case, you have a bigger problems. So what would happen if the attackers could exploit stuff directly in the clients, the client-side code? As I said, this vulnerability is in the gLibc code. Who uses it? Pretty much everyone. There is one, I think, alternative implementation that's done by the guy sitting in there, GetDNS. There's a bunch of other DNS bindings, but they're not really that used. I think the history behind the whole implementation comes from Band 4. It's pretty much the same code for FreeBSD, Linux, and pretty much everybody else. So it's not really varied. And if you find a deficiency in one implementation, then it's very likely it's going to be in the other ones as well. What does this mean is the binding is not really specific just to C programs, since most of the languages just bind to the C implementation and reuse it. So you can pretty much crash Ruby client or Python or what else. So now to the meat of the presentation, how did we carry out the attack? Minor spoiler alert is that we already blogged about this. If you want to see the actual running code or some technical details behind it, you can just search for Cloudflare blog and CV, I don't remember. So what happens in the most basic versions is that the stub client sends a and quad A query to the attacker. The attacker sends, oh, there's a typo, this should be 2048. But it doesn't really matter. The attacker sends an oversized answer, which causes a buffer reallocation. And for the second one, it says, no, this answer is too big, I'm just going to truncate it. So what the client does is really interesting, since it's trying to be smart, and does the right thing and reallocates the buffer to accommodate for the bigger size. But the next packet that comes with the truncation bit set says, oh, I'm going to retry to TCP, but I'm going to be smart enough and reuse the same buffer. Well, it turns out it reuses the size of the buffer, but it still keeps pointed to the old statically allocated buffer. So whatever comes in the final answer and is bigger than the 2048 bytes, it's going to write past the buffer boundary. So here we go. These orange parts are pretty much a thing that are constant in all the variants of the attack. There has to be an answer that's bigger over 2K. There has to be a retry, and then has to be a final answer with the attack payload. So the attacks varied. One of the problems that might happen right now is, for example, Ubuntu uses DNS mask, which is a kind of DNS forwarder, but the attack doesn't change very much since the DNS mask just transfers whatever the attacker sent back, like 1-1 mapping. So slightly difficult situation. If they run something like forwarding unbound, which scrubs whatever traffic gets from the upstream, then the scrubbing forwarder might be smart enough to realize that 2 kilobytes in a plain DNS over UDP is not going to fly, and it's going to send TC instead. So what do? We just move the whole attack on the TCP completely. So when the stub client sends first the 2 queries, then we respond to both with the TC1, which forces the client to revert to TCP and do the whole thing again. The only thing that's different is that we can't just do TC truncation bit on the TCP answer. That doesn't make sense. So what we do instead, we just break the connection and the client's going to retry. So all the condition holds. The big answer is all these attacks so far were targeted. You have to have at least some sort of direct visibility to the actual client. The skeleton key in this is, can we just write a service, then send the clients a name, and they're going to resolve it and crash, like off-path attack. Turns out we can, but let's figure out why first. So recursive implements some sort of asynchronicity in the whole DNS resolution. So on one side, on the client side, you have just 1 or 2 queries, but on the other side, on the right side, it makes a bunch of different requests and scraps the answers and then caches them and then just sends them back. So obviously, the first most simple variant of the attack is not going to work since DNS over UDP, the basic one without the DNS extensions, doesn't do 2K packets. But at least we can do one thing and circumvent caches with the 0 TTL. Unless the recursive enforces a minimal TTL, this is going to work. So we can still at least control the timing. So let's try a different approach. Like with the previous scrubbing forwarder, what we did was we induced a reset. But how do we do it with the recursives? It's, the attackers don't have a control over what the recursive does with the client. They just see one part of the things. And I think this is the point where I hand it to Jamie, who's going to explain a couple of real-life recursives that we have broken this so far. Oh, one more slide, sorry. So just to recap from what you know. So as an attacker, we control the TTL. So we control caching and make sure that the queries and answers flow in a way that we want them to. We also control timing, so we can answer one query, but still hold the other one and do something in between. And we can also control the way client talks to recursive via the oversized answers. So whenever we say the answer is going to be bigger than 512, and then we know that the recursive is always going to upgrade to TCP unless the client is speaking eDNS 0, which the gTLD client doesn't by default. So here is the revised version of the attack. So what we're going to do is the middle orange line that's different, we're going to send the first oversized answer. Then we somehow send the reset, which makes the client retry over TCP, and the recursive delivers the attack payload over TCP. What the attacker does is the first one uses TTL0 just to make sure that after upgrading to TCP, the recursive is still going to ask the attacker And for the quad A answer, it's going to stall and do something in between. Great. Jamie?
Hi, everyone. Thanks, Merrick. I'm Jamie. So I'm going to go over a little bit of what worked and how we did this over real resolvers. Some of the suggested mitigations were kind of crazy, which is what got me interested in this. And I'm not like the DNS person. He's the DNS person. I'm an InfoSec person. But they were putting all these suggestions out there for mitigations, and I was like, these are all crazy. Like, why would you limit this? Like, it's nuts. And I called like a round table at a Saturday night with all the SREs, and I was like, we gotta patch this like everywhere, and they did not like me for that. So, Red Hat was like, they did great research, by the way. They said to avoid A and quad A queries, but it's just dumb. And like avoid like EDNS 0, which is like, okay, yeah, bad. So it is exploitable, but how exploitable really? So we decided to target DNS cache for a specific reason. It holds 20 concurrent connections in a first in, first out basis. The reason for this is to stop attacks like Soloris, which will hold on to connections to clog up the pipeline. So we're able to sever the connection as long as we wait out the, or just keep making requests. And that will sever the TCP connection, forcing the retry. And as soon as that happens, that's like game over. So, yeah, game over. You win. And we were able to do that remotely. And sure, so we got a crash. We were able to do that consistently. So everything really hinges on being able to sever this TCP connection. So what we did was try different resolvers. One of them was OpenDNS, and we got a hold of OpenDNS people. Brian is here actually, and we spent a long time hacking on OpenDNS with him on a Friday night. But they were not vulnerable because they're actually based on DNS cache, but they were not vulnerable to the same attack. But that doesn't mean that they're not vulnerable. Like anything that can be pushed to the state where, any resolver that can be pushed to the state where the connection is severed, then it opens the door for exploitation. And yeah, we were able to do that with Bind9 too. Since Bind9 likes to just throw assertions everywhere, we basically took a certain CV. I'm not going to mention it because I think they told me not to. So basically it's the same attack, but you throw a packet at it that just severs the TCP, or that crashes it, therefore severing the TCP connection. And then you get the retry, and then you send your payload. And then it's game over again. We see the winner. And so to successfully exploit this, it's really, really, really difficult. To actually weaponize like a real exploit for it is that actually like executes code. Like sure you can crash everything you want, but that's boring. We want remote code execution. You have to know a lot about your target. It's not a simple /hack. It's not like targeted at anyone. Sure, you could write something most likely for, you know, IoT stuff. Probably is a good would be a good start. But yeah, there's lots of variables like sometimes like the A and quad A queries like show up in a different order, and like I'll get an NS, like and it's just like messes up my whole exploit. So your exploit has to be like perfect and spot on for this to like actually work. But if you deliver the payload, like it's just basically back to smashing the stack for fun and profit. There's really too many uncontrollable variables here. I mean, you trick people into visiting malicious sites and have their name servers like pointing to ones that are broken and controlled. Yes, but it's still feasible, and we don't know if this is being exploited or if it has been exploited, which is like the scary part. The MacGyver effect, which is what Dan Kaminsky said in his blog, is that bugs only get better. And I think over time, like, we might actually see this bug pop up again. And because there's so many legacy devices that will never ever update glibc. And I'm sure there's like there's boxes in all of your companies that have vulnerable versions of this. It's going to be around for years, and bugs only get better. Yeah, IoT, CPEs, if Mirai, like the Mirai botnet were to use it, like could be in a lot of trouble. But yeah, that's really about it. Some of the mitigations, though, was probably the best mitigation besides patching it, please patch, is having a minimum TTL of like even just 1 or 2, 5 seconds. That's probably like the best mitigation besides patching it. But at the same time, we still have all these Internet of Things devices that will never ever get patched. And yeah. Questions?
What's my bank balance? Oh, no, wrong question. So you say it's not been, the previous slide, something about no way of telling if this has been exploited in the wild still. How would you tell?
Because I don't know.
I mean, how could you tell if it was exploited?
It's a good question. I mean, I do know that when I did the Bind 9 setup, I was on Amazon on a couple different EC2s, and they caught on to it. And so I guess there are ways of detecting it. I mean, I'm not sure exactly. Maybe Merrick could probably answer that better.
Oh, it's just a comment. I think it kind of depends on how smart the attack is. So
I'm sorry, you're going to either have to...
Yeah, I was just saying, I think it depends on how smart the attack would be. If you see binds crashing all over the place, then we have some sort of the idea that something's going on. If you see browsers crashing, then then gives it out. But if the actual attack payload was perfect and it just executed code without crashing the application, then how would you tell?
Right, that's kind of the question is how do you tell? And how do you detect the latent nature of this in systems? Because you say if enough devices are infected by the botnet, how do you tell? I mean, can you tell if a device is infectable, if it's pristine, or has it been already compromised? Is there a way to find that out ahead of time before it goes malignant and spreads?
Well, there is no necessarily botnet out there. This is just theoretical.
Well, Mary was out there, and
Right. I'm just saying if they were using this vector, but I mean, obviously you could look at the message and see that bind is crashing or your resolve is crashing or glibc's whatever program is crashing that's using the stub resolver.
okay, so I'm not really going to look at bind or my browsers. I'm actually looking at the CPE devices and the IoT devices. Is there a way to examine the code base and say, that's the vulnerability there, this is where we're going to get hit? If you guys are going to, since there are what, four basic code bases for IoT devices, fix that piece of code right there, take the extra hit in the real estate, make it a little bit bigger, cost a nickel more, but prevent that from happening for those kinds of CPE devices. Can we do that?
Yeah, absolutely. I mean, if you just introduce the packaged version of glibc.
So I don't really like this vulnerability, or maybe some of the messaging around it. So this is a vulnerability introduced in a specific version of glibc. I don't remember the exact details, but within the past few years, and it gets patched later, just in 2016.
It was in February.
Yeah, it's February this year. But glibc is a specific DNS resolver used on specific platforms, right? And these platforms are mostly server-oriented and desktop-oriented, except for the fact that not that many people use Linux on the desktop, right?
Sure, but they have Linux in their routers.
You're talking about like CPE routers, or so? I mean, how common is glibc on these horrible IoT and CPE devices? I think, in terms of optimizing the number of flash memory cells on the devices, people tend to prefer C libraries that are not as big as glibc, right?
Sure, lots of people use UC libc, muscle libc, a few others, but I'm not sure, was UC libc affected?
I think it was. I think you have a good point that this affects a specific class of devices using a specific version of a glibc library. At the same time, it was quite common. I don't have any numbers to back it up. Is it on 20% of the routers? Is it 10%?
It was on dozens. If you look at the CVE itself, it's confirmed on pages worth of routers. So, I mean, your question, how many, that's how many actually confirmed just with the CVE. So I would imagine at least twice that many.
Okay.
Yeah.
Thanks, guys.
Thank you.
That being all, time for a break. We'll meet back here at 4 o'clock. Thanks a lot.
We're about to start in 2 minutes for the lightning talks. So good afternoon. We're about to start the lightning talks. We're going to have 3 presentations, 5 minutes each. We're not going to have time for questions. So if you have any questions to the presenters, please catch them after the presentations. And we're going to start with Mr. White. Andrew White.
Good afternoon. I'm Andrew White from Charter Communications. And first, before I say anything, while I'm here representing Charter, my comments today are not Charter's official stance, and I don't speak legally for them. Before I get started, I want to tell especially the operators here a joke about IPv6, but you're probably not ready for it. So I just want to talk a little bit about DNSSEC today and operationally what it means for operators and people like us involved with DNS. And I'm not bringing anything here that's not already common knowledge in the community among you, but among operators like Charter and other large operators of recursive cache servers, it's a pain point how to get it deployed and why people want to use it. I just want to talk a little bit about that. So one issue that we see today with DNSSEC is that it provably makes DNS reflection attacks, for example, worse. Records are larger, and any query can be, in some cases, 8 kilobytes or larger, and so amplification is an issue with DNSSEC. Stub resolvers today do not generally validate the DNSSEC responses, as we all know, so really the chain of trust only goes to the recursive server and not to the client. Stub resolvers don't tend to validate responses. Doing so would also cause quite a bit of extra DNS traffic. And this allows undesirable behavior like NX redirects that appear to be trusted from the ISP, and that may not be wanted. DNSSEC does nothing to resolve many of the privacy issues we've already discussed here in the presentations today and yesterday. And there's really no motivation to implement DNSSEC for an operator of a recursive cache server because there's no user demand really whatsoever. So what are the potential solutions? DANE is a potential solution as per RFC 5934, management of DNS source trust anchors. We could say that stub resolvers must validate DNS responses if root trust anchors were preloaded, much like we preload browsers today with trusted certificate authorities certs. We could ditch DNSSEC for DNS over TLS, which personally I think is the best solution. And there's a few other options mentioned which are other potential solutions to the problem. That said, the only way DNSSEC or something like it, like DNS over TLS, is ever going to happen is if the browsers or the operating systems force it upon it. So those of you who write stub resolvers or write browsers, please start thinking about the problem. I want to thank everybody today, and that's all I got, except for 2 quick things. RIPE Atlas is great. We love their data. If you don't have probes in your network, please get them. And I am working today at Charter about the problem of V6 synthetic response as per RFC 1912. If any of you are interested in that, I encourage you to find me after the presentations today. Thank you.
Now we have Mr. David Conrad.
Hello, everyone. I was encouraged to write this up yesterday as a result of one of the talks.
And basically this is how you can request changes to how the root zone is actually managed. For the people who actually want to go back to sleep, including myself, this is sort of the too long didn't read. In the past, to be honest, no one was really quite sure how to submit change enhancements for the root zone management process. So essentially it defaulted to NTIA because of the IANA function contract. Whether or not you thought the IANA function contract was relevant was sort of not important because at least there was somebody to blame. Now, still nobody's really quite sure. We're still working it out. But it's probably has something to do with a new body called the REISE. And yes, we did try to find a B for that acronym, but weren't able to come up with it. So, before the transition, anytime we wanted to make a change to the way the root was managed, we didn't really know how to go about that. For example, in signing the root back in, started around, 2005-ish, 2006, folks in the technical community sort of jumped up and down and said, hey, we should really sign the root. And nothing really happened. Even got to the point where I made a tragic suggestion to Paul Vixie at ISC that, how about something to get around this fact that we don't have a signed root, and that turned into DLD, and I will forever regret that. But moving forward, after a little while, even the ICANN board started jumping up and down, and other bodies, SAC I think, got into the mix and said, hey, let's really sign the root. And there's a little rustling around, but nothing really happened until the Kaminsky attack. That resulted in people's hair catching on fire and running around screaming up and down. NTIA did a notice of inquiry, eventually asked ICANN and VeriSign to come up with proposals. NTIA went away and ended up picking up the VeriSign proposal and moving forward, and after a couple of years we actually got the root signed. So you might have heard of something called the transition, the stewardship of the IANA functions. There are a bunch of other words in there. As of October 1, NTIA officially goes away and has been replaced with the multi-stakeholder community via the empowered community, single membership that replaces NTIA's oversight of ICANN. This resulted in a whole raft of new entities created and fine lunches and dinners in far-off exotic places for many people. There is a new organization called PTI, which is an affiliate wholly owned by ICANN that actually is to whom the management of the IANA functions has been outsourced. PTI has a board, 5 people, 2 ICANN staff appointees, the president of PTI, and 2 community appointees. There's something called the Customer Standing Committee that's intended to ensure that PTI, as it's performing the IANA functions, does so under a stringent set of service levels. There's this thing called the Root Zone Evolution Review Committee that is intended to review changes proposed to the root zone management system. And there are a whole bunch of other things that have been created that I don't want to get into because, frankly, I get bored and confused. But talking about the Root Zone Evolution Review Committee, so the REISE is intended to provide advice to the ICANN board on changes to the root zone management systems. It's not intended to provide any advice on how the root servers are operated. That has a completely other different committee, RSAC. And the process by which this advice is collected, aggregated, provided to the board, that I don't think has yet been defined. I should actually be clear here. I'm not speaking on behalf of ICANN in any way. This is sort of my personal interpretation, having been involved with this for a couple of years now. I might be completely wrong. I think I got most of it right. But getting back to REISE, the ICANN board will make the decision about what to do moving forward based on input from REISE, among other bodies, RSAC, SAC, people on the street, I don't know. This is the current composition of REISE. Some people who are actually here are members of REISE. Brad is
back there, Suzanne right there, Dwayne hiding somewhere in the back somewhere. Oh, there he is. Are members of REISE Oarc. It has been formally constituted. It has a charter and everything. It's, I guess, discussing when it's going to have a meeting, its first meeting. But it's supposed to cover all of the folks who would have an input into how the root zone is managed. Speaking of ICANN, one of the things that I've noticed is people tend to sort of blur the lines of what ICANN is, and there's really a lot of good reasons for that. ICANN is the community made up of a bunch of constituencies and SEs, SOs and ACs and a bunch of other acronyms. It is the board, 16-member board with some liaisons. It is the organization, the company for whom I work, and it is also the IANA functions operator. ICANN, the organization, does what the community and the board tells it to. This has been reinforced multiple times by the new CEO. We are at your whim. ICANN, the IANA function operator, does what the organization tells it to via a contract, but also ICANN, the community, via the Customer Standing Committee and the Root Zone Evolution Review Committee. So, with all of that background, so how do you go about requesting new features? I don't think anyone really knows, but there are some options. One, you could try to say things like shame on IANA, but be aware that IANA staff's ability to do things is actually highly constrained. For example, before the transition, the actual algorithms by which IANA was able to support DS records was specified in the contract. Changing the contract was quite complicated. There was a lot of resistance to it, and especially as we came closer to transition, we didn't want to do anything that might suggest that we were moving ahead with the transition before the U.S. government had finally indicated the transition should move forward. You could get the IATF and the IAB to say, go forth and do something. That is possible, but whether it'll work or not is sort of unclear. An example would be the IAB statement on the RPKI route. You can go through ICANN's board. That is probably the decision maker now looking forward, but in reality it'll probably just bounce that to REISE Oarc for advice, or you could go through the constituent bodies of the REISE Oarc to ask for a change to be made. For example, support ECDSA or perhaps GOST in DS records in the root. We'll see what happens. And with that, thank you.
So we invite Perry Manderson to talk about the CBOR format.
Yes, I work for ICANN too. But I'm not going to talk about policy stuff. That's his problem. So this is on the back of a presentation or building from a presentation that Sarah did in Buenos Aires at the workshop there, and also keyed off of the discussion that happened yesterday, because I heard a lot of people saying stuff about PCAPs. And I think we've all realized PCAPs aren't that much fun to move around. And that's one of the things we had a problem with. So in my day job, I'm responsible for LRoot. We have 158 Anycast instances. We have buckets of data. We've got around about 60,000 queries per second on average. And we like to actually bring that back and analyze that, surprisingly enough, for statistics and for other things that happen. So with all that data everywhere, moving PCAPs, oh my God, is it hard and painful. So instead of PCAP, we wanted to do something else. So you look at all the bits that are really kind of interesting and groovy in the DNS message, and you go, well, I want to keep those bits, and maybe a few other little bits, and I only want to ship that back for analysis. So we picked up CBOR, Concise Binary Object Representation. Oh my goodness, it's standardized. It's open there. Great. It's also got a whole heap of tools, APIs that are very, very helpful. So we created a format using CBOR to ship the data back. So do we have running code? Yes, we do. It's now running on LRoot. So we actually wrote a new, what we call a compactor, which is just like a collector, listens for the packet, and so instead of outputting PCAP, outputs this new format, and we ship that back. So in terms of query and response, CBOR format is a 70% smaller than PCAP. Now, I don't know about you, but that's a big win for me. And I can't tell you how stoked, absolutely stoked I am how efficient this is. It is brilliant. So the cool thing here is once we get that CBOR back, we can still synthesize a PCAP. There are a few quirks we've got with name compression because some servers don't actually produce, and I'm going to be really polite here, it's not consistent. It goes either ways. So that's you can talk to me after over a beer and I can help explain some of that. Where are we going from here? Well, coming up, we're going to do a draft in IETF land really, really soon. And we are certainly also looking at sending data to OARC as a trial for our AS112 servers. And we plan on very soon releasing this on DNSstats.org. So you can grab it, look at the code, and have a play. If you're a little bit impatient, that's what it looks like. Oh my goodness, looks like a whole heap of DNS stuff. Cool, huh? Now, if you're observant, you'll notice that things are kind of linked, like almost a relational database. So that means you can have pointers to other things. So one of the things we've all kind of noticed, I'm sure, in DNS is it's pretty damn boring, really. People ask for the same things all the time. So if you start looking at things that are asked for the same thing all the time, you don't have to repeat that like is repeated in a PCAP. So that's where a whole heap of the efficiency comes in. And that's pretty darn cool. And I think I'm basically done. Thank you.
And well, that ends up all the lightning talks. So we're back on the regular presentations. We invite Cyprian Cosma for his presentation about UDP buffer stunning.
Hello, my name is Cyprian Cosma. I am a system development engineer with Amazon. I will present a talk about UDP buffers tuning. This talk only refers to UDP receive buffers for DNS production web servers. First of all, what is the importance of getting the buffer size right? If the buffers are too small, you will drop packets during peak loads. I don't know exactly what. And you won't be able to cope with spikes in traffic. This means a poor customer experience and also an inefficient use of your infrastructure. If the buffers are too large, of course, you will get an increase in latency. So this ties up with some questions that were before. What are the proper timeouts that you should consider in DNS? And I mean, it's no point in answering if your client has already timed out. And you will also be slow to fail. You will detect failure in your server too late, and you will drop a whole bunch of packets that were cached. Usually, we think about traffic in DNS in terms of queries per second, and we scale and monitor and think about our infrastructure. I don't know what's happening with this presentation. Can you let me jump the slides here? So we need to find a way to move from queries per second to bytes, since buffers are measured in bytes, kilobytes, etc. This usually is done by multiplying the query per second number with a mean packet size and with a scaling factor to account for inefficiency in the operating system. I am going to try to look at what's the proper value for this scaling factor. Okay, good. Okay, great. And also have a look at what is the buffer allocation and the accounting strategies. For all these tests, I use Amazon Linux with a range of different kernels. So all the results only, apply to this. We've used IPv4 and IPv6 transport. Just a very brief overflow of the packet receive workflow in Linux. This is very simplified, so if you are into device drivers, please don't cry. It's just the NIC and driver, after receiving a packet, will copy the packet using DMA into the main memory, taking a reference from a ring buffer of available SKBuf structures. All these structures are pre-allocated by the kernel. They are using the slab allocator for speed. After the packet is copied, the kernel will be notified to interpret it and move it up the stack. All this process is optimized for speed, meaning that once memory is allocated for a packet, the kernel tries never to copy the data or to deallocate the memory. So speed is it's optimized for speed, but not for memory consumption. If we take a look at the SKBuf structure, this is the most important structure in the networking subsystem. It has a control structure, which is on the left. The packets are in a double linked list. It has a whole bunch of metadata, and then it points to the actual packet data, which is pointed in another part. What's important, so in DNS and for small packets, each query will correspond to an SKBuf structure. In TCP, and if you have fragmentation or other use cases, this might not hold true, but for UDP queries coming into the server, this is almost always true. As I said, once the structure is allocated, it is kept in memory even until the data is read by the application. The pointers, head, data, tail, will move to different parts as the packet goes up the stack, but the memory won't be freed. There is also a secondary structure, SKB shared info, which is at the end of the packet data, and which is used for things like cloning and fragments and stuff like that, which are also usually not used in DNS servers. What's the importance of this structure? One of the fields in this structure, true size, is the value that is used by the kernel to report on your buffer allocation consumption. This is a sum of three fields: the size of the SKBuf structure itself, the size of the SKB shared info, and the packet data. Since all these structures are slab allocated from a pool of predefined buffers, they will always be larger than what's needed. You can see the status of these buffers in ProgNet UDP. If you look at this line, you will have the IP address and port in hex network order, and in RxQ, in the RxQ field, you will have the current value of allocated buffers for this socket. This is also in hex, so 300 here will correspond to 768 bytes. Of interest is the last field, drops. This is how many packets were dropped from this socket because the application did not read it fast enough. This is a counter which is only incrementing for the life of the socket. I would like to discuss briefly the kernel parameters which can control the buffer size. You have netcore RMM max, which is the total amount of memory for a single socket that can be requested. RMM default, which is the size that it will be allocated if the application does not request a special value. And also net IPv4 UDP mem, which is the total amount of memory for all sockets on this system. This last value is expressed in pages, so it has to be multiplied by 4K to get the actual values. If the application doesn't want to use the default value, it can call a setsoc opt on that socket and get another value. Here I had a short live demo, but it wasn't possible, so I've just added this slide. The setsoc opt doesn't actually do what most people think it does. I have this short script to give you an idea. What I do here is I print the RMM default value, so the default buffer that all the sockets will get. I read it with the getSoc opt. I print it, and then I set again the same value. You would expect all these values to be the same, but in fact are not. The value that you set with the setsoc opt will be doubled internally to account for some overhead. This can get the funny effect. Most applications and most DNS server actually do a piece of code like they get the current buffer, size, they compare it to a preset, and if it's lower, they will set it there, which will get you double this buffer. I know that people here love to pick on bind, so I won't say that they do it, but they do it. Okay, so here we have a first test. I have sent a packet with increasing payload sizes from 1 byte to 4,000 bytes, and I have recorded the buffer size as the kernel reports it. As you can see, this graph is not linearly at all. It only has a couple of values. And also what's interesting that even for a payload size of 1, the buffer size is 768. So from the setsoc opt thing, you would imagine that the overhead is around 2x, but it can be much, much larger. Using different kernels, you will get slightly different threshold values. So sometimes you go for the first step, you would go to 69, sometimes you would go up to 100. This depends on how the slab allocator in that kernel is configured, and also from that pool of available buffers, what can the kernel get at that point. So most normal incoming queries are about 50 bytes long, so they fall into the first bucket. But some of them can go to the second one, like an IPv6 reverse is longer. If you have some options set, it can go higher. But for the large percentage of incoming queries, you are in the first or the second bucket This is the same graph in IPv6. As you see, the thresholds modified a bit, but the whole idea is the same. Trying to get a feel on what is all this space used for, I've used System tab to have a look on all incoming packets and the buffer allocation for a certain socket. So you can see the socket address from that ProgNet UDP for your DNS server, and then you just attach a probe on SOC-Q receive SKB, for example, and you can inspect all these structures live. The size of skbuff itself is 248 bytes, and the size of skb shared info is 320. Whatever you do, these two structures are allocated for each incoming query. And then you get a variable data structure which holds the packet data, including the L2 and L3 and L4 data, which never gets deallocated until the application reads the contents and the whole skbuff is deleted. As you can see, the skb through size points to 768. This is done for a 50-byte payload packet, a normal query. There is some wasted space at the beginning between data and head, and also between end and the tail is a whole lot of unallocated space. So the main point from this investigation are that the overhead might be much larger than you think. If most people assume that it's about 2 times the packet size, for typical DNS query size, this is more like 20 times. And also, if you switch, sometimes if your query size is near one of these thresholds, a small change in names or in payload type, if you now add IPv6 PTRs as zones, you might see a lot of, you would start to use the buffers which are much larger than you expect. Here is a short table in the case of normal queries, so queries that will require 768 bytes of buffers. About what size buffers you would need if you would like to do so many queries per second and be able to cache them for this duration. So if you do 100K and you want to be able to cache 100 milliseconds, you would need a 7.3 megabyte buffer to be able to hold all these packets. Okay, that's it. Questions?
Paul Hoffman, just a brief one, because I'm definitely not a Linux kernel person, but you put up, some of the things that you could tune. You said net.ipv4.udp _mem. There's not an equivalent one for IPv6?
Oh, yeah. Sure.
Okay,
sure.
just checking. I didn't know if IPv6 was special, because it always thinks that it's special. So, okay, great, thanks.
Okay, good, thank you.
Next, we would like to invite Mr. Sebastian Castro to talk about the hunger for Quad A.
Me again. Please get some water. We can hear the waves on the webcast about once get started there, and then it's like a Mexican wave of caffeine going left to right and right to left. Anyway, maybe it's the air conditioning. So this is a short talk. It's intended to be 15 minutes, and I hope it's interesting to you. So it's kind of aligned with the idea of what Vincent presented today, of finding out using data something that went really wrong in the internet. That never happens. So we call it the hunger for Quad A. And all it started with our CTO coming, talking to the operation team, saying, you know, we have this offshore provider that does DNS for us, and the bill from the last month is like 20% higher. So what happened? And that's actually particularly painful where you're paying by the query. So we started to checking for anomalies in the data. We keep our capture of our DNS data for, we have 3 years now. And we also ask the provider, what kind of data do you have that can you provide us in order to go and search and confirm what you're seeing? So the common pattern on this was there was a very large amount of Quad A queries for ns3.dns.net.nz and ns4.dns.net.nz. So what's with that? I need to explain you very briefly how the .nz delegation works. So we have 7 name servers, named ns1 to ns7. 4 of them are managed by us, and they have instances in New Zealand, so they're New Zealand centric. There are 2 of them, NS5 and NS6, managed by one provider, and there is the last one, NS7, is managed by a different provider. I'm not giving names. We don't like to go and put people in shame or something like that. There's no shaming here anyway. So only NS3 and NS4, DNS.net.nz, didn't have a Quad A glue in the root zone because they didn't have IPv6 addresses. So you may think, how you call yourself running DNS professionally and you don't have IPv6. And the thing is, getting IPv6 in New Zealand is not that easy. You may think, what? But this is 2016. How is that possible? And in order to enhance my point, we had a problem like 3 years ago with one of the New Zealand ISPs who deploy a change to the routers, and they completely wipe out IPv6 connectivity to one of the name servers overnight without a warning. So in the middle of the night, we start getting warning, you know, this name server is not reachable via IPv6. What happened? And we raised the problem. Is like, oh yeah, we deployed this change to the core router, and the core and the license doesn't include IPv6. You are, yeah, I cannot swear. But it was a shame, and after a year of chasing them, when are you going to enable IPv6 on this back? Because you had it before. They said, you know, we don't have any plans to have IPv6. Until now, they don't. So we have to actually move the name server from that space to a different provider in order to have the hope of getting IPv6. Anyway, going on the sideway. So how bad was this? So this is a graph that goes back to January 2015. And you can see, and then there's one graph for NS3 and one graph for NS4. So suddenly, in one day, the traffic for that name for Quad A went from roughly 1 million queries per day to 3 million, and then start ramping up to 7 million queries per day for the same query name. And it was, and you see the pattern for NS3 and NS4 is exactly the same. So something went really wrong on that date. So because we have our data, we can actually go and map. We have all these source addresses mapped to ASN, and we found out one culprit that went from like very little traffic to 1 million queries in a matter of a day, and then it starts ramping up. So this is the major culprit, but there's a few others. So because we know these guys, we can actually go and tell can you help us? So this is the combined plot. So the blue one now is this specific provider, and the orange one is the total traffic you saw originally. So this sole provider was, they were generating like half of the traffic at some point at the beginning, and then slightly going up. So we had two options. So one is, please, you guys, can you go and check on your platform why are you sending us millions of queries for the same name? And the other was like, okay, we need to add the Quad A records for these names. But as I said, getting IPv6 connectivity is not that easy. It was not an easy fix. So both things actually happened at the same time. The provider kindly responded, okay, we'll take a look and let you know. And we reused the IPv6 addresses for NS1 and NS2, for NS3 and NS4 as temporary measure until we got real IPv6 connectivity. So I have to go and give kudos to them, to Daniel and Dane from the operations team for making this possible as soon as it was possible. Sorry. So the combined solution. So this, how the problem was fixed. So we have 3 changes or 3 events. Again, NS3 and NS4. So on July 1st, we add the NS4 glue record to the root as a test, and you can see as soon as that record was published in the root zone, not in the parent. We did that in advance. The traffic dropped and went back to normal terms. So there's nothing very interesting to see there. But for NS3, it was more interesting because in July 7, roughly, the provider started to have that the fix they prepared was deployed. And they said, it's going to take probably 1 week, 2 weeks. We have plenty of sites, so please be patient. So there is a big drop first, and then the final drop to normal levels when we added in July 29th the NS3 glue record. So, okay, fix. However, I started thinking, maybe there's some other people affected by this. They haven't noticed. They keep paying the bill. They haven't checked the traffic. So I went to the root zone and checked for the authoritative name servers listed in the root zone that didn't have a Quad A glue. And there are 532 name servers matching that category. And they cover in 330 different TLDs. So it might be possible that one of them actually have some traffic collected, and they can go and compare nodes and see if they were affected by this, and also they will favor it by the solution. So still the open questions is, what the heck happened on February 2015? So Roy Ahrens picked me in the middle of today, and he told me, you know, I check changes to, I don't know, NSD or an unbound or bind in case there's something there. There's nothing. There's no change that seems to be relevant. My take, so my gut feeling on this is a change in a system library in a major operating system that's starting preferring Quad A over A records and was not handling the response properly. So for those not completely familiar with the protocol, when you ask for, give me the Quad A record of this label and that record doesn't exist, you get an empty response. It's not an NX domain, it's an empty response. So they were not respecting the negative TTL for the zone, which is an hour. So someone was trying really hard and not respecting the protocol and doing something weird in there. So if you have an idea, please feel free to go to the microphone and share that with the community. So what we learn on this? So don't shoot yourself in the foot. So IPv6 is important, even if you think it's, oh yeah, no one is requesting that, or there's no demand for IPv6, but you're running a critical infrastructure, and it's very likely you will see customers or clients or users that are using that kind of transport. You need to pay attention to anomalies. We didn't notice this problem until very late. And for example, keeping even the minimal traffic counts will help you. So in this case, we have our big data platform, and we keep all the traffic so we can actually go back in time, run the query, and find out about this. So that was interesting. So if you're familiar with, at some point, Roy again made a presentation about Turing, where he can go and find out things in the past. It's more or less the same idea, but that less developed. So that's me. That was like 10 minutes, something like that. So all good, so we can finish early and enjoy the rest of our Sunday. Any questions? Point one, okay.
Paul Hoffman, I didn't understand if the ISP did something, how could it be something like with happy eyeballs and such? Did you have much communication with that ISP about?
No, it wasn't an ISP.
It was an AS number.
Cloud provider.
Okay.
Leave it that way.
Right. Okay. So that doesn't match your guess at the end of what happened.
No.
As far okay. Okay. Good. And you didn't have enough interaction with the cloud provider to find out what they thought they were doing and what they fixed.
It was like, can you tell me what kind of fix did you do in order to improve the situation? And the answer was like, ha.
Got it. Okay. Did it have an exclamation mark with the ha?
Yeah. There is a possibility.
Sure. If they happen to be in the room, maybe ask them.
Yeah.
Jeff Houston, you have to make the distinction when you start thinking about end-user systems between the browser and the OS, because the browser actually handles the DNS differently than the underlying operating system these days. And as far as I can recall, nothing really happened at the start of 2015 in terms of what browsers do. The browser you've got to worry about is Chrome, because that's about 68% of the end-user eyeballs. Mac OS, 10, 12%, it's not very big. Now, the general behaviour is, if they recognise they have a working V6 interface, and that's kind of the criteria, the browsers will spin off a query for A and Quad A as simultaneously as they can.
Yeah.
So you'll see the two go out pretty much back to back. And depending on when the answers come back and their own biasing, happy eyeballs, they'll go and make a connection on one protocol or the other. But there's nothing inside that kind of behaviour that would trigger what you're seeing on the date you're seeing it.
You're absolutely right.
Right?
Yes.
So what you should have seen, not right up at the root there, but in your sort of well-used zones, trash.New Zealand or whatever, you should have seen sort of A and Quad A queries that roughly correspond to the amount of V6 out there in the user space.
Yeah.
And as there's more V6, you'll see more Quad A queries, but that's about it. There's no correlation between operating systems and what you're seeing as far as I can tell, nor should there be.
Yeah. And adding on that, you're absolutely right. So it couldn't be happy eyeballs because they're querying for infrastructure records. So it has to be something different.
Yeah.
Hi, Brian.
Hi, my name is Brian Summers from OpenDNS. I might have a confession to make. So back in April 2015, we fixed a bug in our code that, if I remember correctly, it's a long time ago and I can't quite tell from the Git show that I've been looking at. But we used to have some code that would look up NS addresses, and if it found an A address, it would be happy and off it would go. And if it didn't find an A address, it would be unhappy and it would go and look for a Quad A address. And I fixed that in April 2015, but I seem to remember that there was an issue with the fix where it then got confused as to whether it was looking up an A record or a Quad A record. So if it was getting no response, or no data, I should say, from the Quad A record, it may have decided, I just looked up an A record and I didn't get a response, so it's time to go and look up the Quad A address. So it might have been coming from our resolvers. Have you any data on what was actually sending you these queries?
Yes.
Was it us?
No.
Okay.
No.
Maybe it was somebody in between us.
So, yeah, for the record, the provider on the slides is not OpenDNS.
Okay. Well, that's
But
good to know.
I can search back and see how the traffic pattern changed from your sources by deploying the fix, but it's not you.
Okay. Thanks.
All right, thank you.
Well, and last but not least, we're welcoming Mr. Fujiwara to close this round of presentations.
Hello, I'm Kazunori Fujiwara from JPRS. Today, I will talk about RFC 2181 ranking data and referral glue importance and new resolver algorithm proposal. This is my presentation summary. Parent side NSR set creates zone cut and new zone. And the parent side NSRs and glue records are all information to access servers for child zone. However, parent side NSR set may be overwritten by child zone apex NSR set. Glue records are also overwritten by authoritative data. And I would like to propose new resolver algorithm. It only uses referrals and glue records with additional name resolution for auto-veric name server name to iterate. And resolvers answer authoritative data only, and it will update RFC 1034 and RFC 2181. And sources definitions are RFC 1034, 1035, 2181, and 7719. Current definition, referrals and glue records. Small circle shows zone cut and delegation, and parent side NS makes cut, and the parent side NS is referral. Referrals and glue records point child zone, and they are unauthoritative data. And zone apex NSR set is authoritative data. And zone cut. RC 1034 section 4.2 describes that after all cuts are made, each group of connected namespaces are separate zone. In other words, cut makes new zone. Who makes cut? RC 1034 section 4.2.1 describes the RRs that describe cuts around the bottom of the zone are NSRRs that name the servers for the subzones. In other words, parent side NSR makes cut. And since the cuts are between nodes, these errors are not part of the authoritative data of the zone. In other words, parent side NSR set is not authoritative data. And then, and should be exactly the same as the corresponding errors in the top nodes of the subzone. In other words, parent side NSR set and child zone apex NSR set should be the same. Next, parent side NSR set. RFC 1034 section 4.2.1 describes that this is parent zones have all information needed to access servers for their children zones. In other words, parent side NSR set and glue records are all information to access servers for child zone. And RFC 1034 section 4.3.1 describes resolvers return either an error or answer but never referrals. In other words, parent site NS RSet is referral, and referrals must not be used as names resolution result. Next, delegation. RC 7719 describes that delegation happens when an NSR set is added in the parent zone for the child origin. And RC 1035 section 7.2 describes that the NSRRs making delegation. In other words, parent site NSR set makes delegation and zone cut and new zone. Referral. RFC 1034 section 2.4 describes that resolvers pursue the query using referrals to other name servers. In other words, referrals are used to pursue queries to other name servers, not child zone apex NSR set. And RC 2181 section 6 describes that the existence of a zone cut is indicated in the parent zone by the existence of NS records, specifying the origin of the child zone. These are summaries of referrals defined in RC 1034 and 1035. Parent site NSRZ is referral, and the parent site NSRZ makes zone cut, delegation, and a new zone. Referrals and GRU records are all information to access servers for child zone. Referrals and GRU records are more important than zone apex NSRZ to iterate. Referrals and GRU records are not authoritative data. Authoritative data around cut is the zone apex NSRZ in the child zone. Next, current resolver algorithm. Resolver algorithm is described in RC 1034 section 5.3.3. Number 2, find the best server to ask. Number 3, send them queries until one return a response. Number 4, analyze the response either. Number 4b, if the response contains a better delegation to other servers, cache the delegation information and go to step 2. This procedure caches referrals and GRU. Number 4a, if the response answers the question or contains a name error, cache the data as well as returning it back to the client. This procedure caches authoritative data. NSR set at the zone apex may be cached and it may overwrite referrals and GRU. And this picture shows parent NS and child NS mismatch. In the picture, in example TLD, child example NS1. However, in NS1 or NS2, child example NS2, and it's very broken configuration. NS1 have www example A, NS1 www example A and NS2 www example A are different. In that case, first resolve www example A returns from NS1 with example NS1. Next, if a stub resolver resolve child example NS, then child example NS is overwritten by child example NS2. Second resolve www example A returns from NS2. It's unpredictable and unstable. And then RFC 21 5.4.1 ranking data. An authoritative answer from a reply should replace cached data that had been obtained from additional information in an earlier reply. Trustworthiness shall be in order from most to least. Next slide. And this table shows RC21 ranking. ranking number 1 is data from primary zone file other than GRU data, and number 2, data from a zone transfer other than GRU. Number 1 and number 2 are authoritative server data, and number 3, the authoritative data included in the answer section of an authoritative reply is an answer that matches the query. And number 4, data from authority section of an authoritative answer. This data is attached to NS resource record in number 3 answer. And number 5, group from primary zone or zone transfer is authoritative server data. And number 6A, data from the answer section of a non-authoritative answer. I cannot understand the case, but it may be cached answer. And number 6B, non-authoritative data from the answer section of authoritative answers may be additional answer. And number 7A, additional information from an authoritative answer may be additional information. And number 7B, data from the authoritative section of a non-authoritative answer is referral. And number 7C, additional information from non-authoritative answers are GRU records. Then remove authoritative server data and rewrite. Then ranking data in resolver may be this list. Number 3, authoritative answer that matches a query. And number 4, NSR set attached in. Number 3, answer. Number 6A, answer from cache. It may be misconfiguration. And number 6B, non-authoritative data from the answer section of authoritative answers. They may be RRs that is synthesized by CNAME RR or CNAME generated by DNAME. Number 7A, additional information from an authoritative answer. They may be A or quad A RRs that matches MX exchange field. And number 7B are referrals, and number 7C are GRU records. And there are problems of ranking data. Referrals and GRU records are overwritten by number 3, authoritative answer that matches a query, and number 4, NSR set attached in number 3, authoritative answer. This overwrite do not always occur and will break referrals and GRU records are information to access servers for child zone. And some implementations have complicated code to handle number 4, NSR set attached in authority section. And after the override, name resolution results may be changed. And RC2181 ranking data is deemed all data, authoritative, non-authoritative, referrals, and GRU is merged into one. It may be used as an answer from resolvers. Non-authoritative data, referrals, and GRU records shouldn't be used as answers. And recent implementations answer authoritative data only. And this picture shows parent NS and child NS mismatch again. In that case, answers from NS1 contains www example A in answer section and child example NS2 in authority section. And data from authoritative section of an authoritative answer is higher rank than referrals. And if resolver cache had a referral, however, the answer will override the referral. And this override causes a problem. There are problem happened by this override. CVE 2012-1033 ghost domain names. Bind and other software affected by this behavior are so affected because of the inherent long-standing design of the DNS protocol. The attacks used updates of NS RZ attached in authoritative answer and from bind9 changelogs. This bug are fixed by restricting the TTL of NSRZ to no more than that of the old NSRZ when replacing it. And this fix, after this fix, DNS complexity increased, I think. This is summary of RC 2181 ranking data. Ranking data seems to be written in with an assumption that name servers, resolver plus authoritative server have single cache, maybe bind 8. And recent implementations have complicated functions. Answer authoritative data only and careful check to accept responses from authoritative section and assurance section. Then I would like to propose new resolver algorithm. Resolvers answer authoritative data only. Number 3, authoritative answers that match queries. And don't answer referrals and guru records. And referrals and guru records are the only information to find name servers for child zones and additional name resolution for out-of-basic name server names. And don't use zone apex NSRZ for name resolution. Guru records are used for corresponding delegation only. And previous zone files are treated as answers from authoritative servers. They are treated as static authoritative data, referrals, and guru records. And I would like to propose separate caches to authoritative data cache and referral guru cache. Referral guru cache may be established by RC 1034 and needs further considerations for negative caching and DNSSEC and DNAME. And to implement resolvers, prior zone files and root hints is imported to referral cache. Priming updates the referral cache and authoritative cache. And resolving. Search QNAME QType from authoritative cache. If it's valid, return it. And search the closest enclosure QNAME from the referral cache. It points referrals and guru records or error. If referrals contain out-of-basic name server name, resolve them. Number 3, send QNAME QType queries to name servers of the referral. Number 4, analyze the answer. Number 4a, if it contains authoritative answer, copy it in authoritative cache and answer it. Number 4b, if it contains referrals, copy it in referral cache and go to step 2. Otherwise, do error handlings. These are characteristics of the proposal. This proposal does not change resolver algorithm described in RC 1034, except updates of referrals. And it separates authoritative data possible to answer and referrals used to iterate DNS3. And no special ordering, trustworthiness ranking. And it offers more stability of name resolution. Results of traditional name resolution will flap if NSRZ are different between the parent and the child. First time, referral is used, and second time, zone apex NSRZ may be used. This algorithm is similar to traditional algorithm when the cache is empty. And there are issues of the proposal. TTL control of zone apex NSRZ doesn't work. However, override of the referral doesn't occur always. TTL control may increase queries to TLD, and it will update Dns Oarc RFCs. And root zone case, root zone is special because it is not delegated. And root hint and priming are exceptions because priming replaces preconfigured root hint by root zone apex NSR set. And they are authoritative data. Then I did experiment of the proposal. I made a simulation program and it will use captured packet. The simulation program reads both answers from authoritative and stub queries, and for all stub queries, it simulates resolvers with cache and output result. And the program compares responses and count authoritative queries. And I used packet capture around binary resolver. And 2 days packet capture at a university. And 20 million client queries in 2 days, and 8,000 clients, and 7 million answers from authoritative servers. And this is experimental environment. And the resolver simulator reads answers from authoritative data, authoritative servers, and query generation and response comparison program reads stub queries and stub answers. And this table shows example result. Do answers match with binary? Answers from CDN valid. They are merged and treated as matched answer. And unmatched answers, 375 were answered from another server rewritten by Zone Apex in NSR set. And most of all answers matched with captured stub answers, except unmatched answers, and proposed resolvers may work, I think. And this table shows number of queries to authoritative servers, and proposed algorithm sends smallest number of queries to authoritative servers. And there are previous implementations. I heard that some software implemented similar algorithms. Nominum software and Mara DNS left good. And there are no effects to DNSSEC. DNSSEC validates authoritative data only, and DNS doesn't validate referrals. And there are no effects to QNAME minimization because answers from authoritative servers do not change. And conclusion and future plan. RC 2181 ranking data may be obsoleted, and I proposed a new resolver algorithm, a new data trust model without a complicated ranking, and it only uses URL and GRU records with additional name resolution for auto-veric name server names to iterate, and resolvers return authoritative data only. And I evaluated the proposed algorithm, and it seems to work in simulation level. And I would like to submit an internet draft this month. Do you have interest? And that's all. Thank you.
Hi, this is Andre from CZNIC. I see, well, this is a very interesting proposal, but it has one problem, and it's deployment. Because by trying to circumvent the level of craziness in the DNS, you would create only more craziness. Because then you would have some DNS resolvers deployed with the new algorithm, some with the old. Some zones would respect the new algorithm, some would respect the old, and they would have to mix together. So unless you have a magic wand that would magically upgrade all the DNS servers at the intranet, and in this case, I would love to have that magic wand as well.
Yes. Resolver's gradual implementation is okay, I think.
But the problem is that you wouldn't be able to switch to it in next 10, 20 years anyway. So, and that's realistic, because if you look at the deployment base, that something like 10 years is normal. And it would only create a more mess in the DNS. And since we've been implementing the DNS resolver, I've seen so much crappiness in DNS that it makes my eyes bleed. So I would love to have it, but I think it's unrealistic to think that it would be ever deployed. So unless you think about the deployment plan, then to say it from the other point of view, I would definitely have an interest if you have a solid deployment plan, but I haven't seen anything in your proposal like that.
I think I need implementation, and if it works well, then I would like to deploy. Thank you.
Hi there, Brian Summers from OpenDNS. We kind of bumped into this this general issue. I think it interacts very heavily with whether or not recursive resolvers actually take authoritative data and, glue data and authority data, and whether they trump the stuff that's already in the cache based on whether or not the TTL is longer and the trust level of the data. We had an issue where, I think it's what you described, where an old name server kept on reasserting its authoritative control of the domain, and it stayed in our cache forever because we looked the domain up enough that we kept on getting these records back. The answer was, in our implementation anyway, to never allow a name server to keep itself in the cache. So name server data, when it's found, if we get additional name server that's a higher trust name server data that's a higher trust level, then we'll use that. But if we get repeated name server data that's the same trust level, we won't re-trump it in our cache. We won't rewrite our cache with the new data, and we'll let it eventually just fall off the end. So in the worst possible case, there'll be days of these name server records, and then eventually we'll be forced to look up the glue again. It's not a perfect solution, but it solves most of the issues around that sort of a problem.
Weber, Nominum. Thanks for mentioning us. We actually have glue segregation since a decade, or a bit more even. It's been deployed around the world, and it never caused a problem. So, I mean, RFC 1034 said you have to cache it. It didn't tell you you have to have one cache for it, or? I mean, I don't see the problem there. And it works, and it's actually a good thing, and it has also certain security mechanisms, security features to it that it gives you. So I'm for it. I mean, if we want to write up something, yeah, we'll be up for it.
Hi, Robert Edmonds, Fastly. So this RFC 2181, section 541, the rank of these, the trust levels, these are the rules that specify the core data model of the DNS, and your proposal is to change them, to rewrite them in some different order. And you didn't really, I don't know, justify the changes in your presentation. You showed a couple of slides on simulating it, and you showed that it reduced the number of queries or something like that. That doesn't seem to be a really good justification for that kind of large-scale change to the data model. Are there any other benefits that we could get from essentially rewriting the data model? And I think, you know, about 8 years ago, there was a very good opportunity to, you know, do something like that, but we didn't. And 8 years ago, there was a much more, you know, important problem than you know, reducing queries. So I mean, is there a good reason to do this?
Hi, John Christoph from DePaul University. I think there's reason for skepticism or to be discouraged by having this widely deployed, but I think that's natural for changing any new thing to something that's already widely deployed. So I would say don't be too discouraged. I think it's worth experimenting more and doing some more work with this, so I encourage you to continue to do that. The one question I would have, and probably can't answer this, but I would be interested to know what would the result of this being deployed would be, is if it would help encourage some of the brokenness that we see inconsistency between the parent and child zones. You see this frequently, and I'm wondering if you did this so that it only did take authoritative data, if some of those who had some of those mismatches, if this would help address some of that issue a little easier than it has been, because it's too easy for things to be fast and loose and half broken as it is. Maybe it doesn't change that much, but maybe it does.
So with this conclude the topics. And for closing remarks, Dwayne Wessels and William, saying the goodbye for this meeting.
Yes, thank you, Mauricio. Just a couple of quick remarks. So on behalf of the DNS Oarc Board of Directors, I want to give a special thanks to our program committee, and especially to our two program committee members who are now forcefully kicked off because they have been on for too long. One of those is my colleague Sean Stewart, who's not here with us today, but the other, as you know, is Sebastian. Sebastian has been our chair for the last 3 years. He really stepped up into the role and did a great job. You know, before 3 years ago, we didn't even have a program committee, so he was in totally new territory and jumping in and did a great job of defining some of the processes and procedures that we use now to evaluate the speakers. And please welcome me in thanking Sebastian for 3 years of chair. So with those term limits up, and just in general, the board will be appointing the new program committee in the coming months or so. If you or someone you know would like to be on the program committee, please consider that. And I suspect that when Keith gets back from vacation, he'll send out a more formal call for program committee volunteers. But please do consider that and let us know. And I'm going to turn it over to William to do the rest of the closing here.
Okay, thanks, Dwayne. I would like, first off, to thank our sponsors, ICANN, VeriSign, Nominum, Salesforce, Netflix, Network Utility Force, NZRS, and Power DNS. Thank you very much for your sponsorship and your support of this workshop. I also want to single out a few individuals, Dave Knight in particular, for supporting our webcast and the logistics. Thank you very much, Dave. I'd like to thank Jerry, Sue, and Dinesh also for their hard work and doing the groundwork for this conference as well, workshop. So thank you very much, guys, and they made this very easy for us. So a couple other things, administrivia. As you're leaving, please hand in the lanyards. You may optionally keep the badges. If you don't want them, give them to us or keep them. Dinesh promised to give somebody a prize if they can prove that they can tear this. So there's a challenge for you. Do the survey. We have the survey up and running already. We'll send a reminder out with the blog posting. I think Dinesh said he would do that forthcoming. And finally, we'll see you in the EU someplace or the United Kingdom. Thank you.